Hello, this is Brian. Welcome to the second video in our distributed architecture series. This non-commercial video comes with the usual disclaimers: no contract, not claiming any expertise, no advice given, etc. It's released free according to the terms of the MIT license. I'd like to propose an approach to maintain consistency amongst a set of pure computers in a distributed application. The approach is called application mining. Let's revisit a slide from the last video showing the software areas. We identified an external access layer that runs on the user's devices. Then we identified some web software, use of the Golem network for heavy processing, and interplanetary file system for serving semi-static resources like app releases. To this point, we have clients and supporting services, but we still need areas to implement the business logic and make this into a distributed system. We'll build on top of Ethereum since that's already a suitable platform for maintaining distributed state, and because Ethereum can move money. When it comes to application processing and data storage, Ethereum has limitations, so we add app-specific areas for these. The fusion of these areas plus an Ethereum full node is what we call an application-level miner, or app miner. For redundancy, we're going to need many of these identical miners operating in parallel, keeping each other honest and evenly sharing the client load. So we have some large number of app miners collaborating as peers to implement our distributed system. For the moment, we can imagine these mining nodes as connecting over a network to the Ethereum system. Ethereum provides the platform to house objects called smart contracts. One such object in our design is a registrar for miners. Another smart contract runs a repeating lottery to compensate miners and keep them synchronized and honest. Miners also provide the services that customers need to interact with the system. Customers will need the ability to make queries, receive notifications of application-specific events, enter information, and make payments. Each miner exposes an external interface to support 0, 1, or any number of clients. Note there's no concept of a client session. Whenever a client has a request, it just randomly selects a miner, so there's no guarantee that a miner will serve two subsequent requests for the same customer. This approach spreads the load evenly. Now let's take a closer look at how miners get paid. Anybody with a computer and network connection is welcome to be a miner. There will be thousands, maybe millions of these over time. Each miner installs the mining software to hold a copy of the application dataset. Each mining node will also have Ethereum, and so will be able to operate as an Ethereum full node. Ethereum automatically creates an externally controlled account, or ECA. This is the account through which the person operating the miner is able to supply and withdraw funds. Miners have to register and put up a performance bond. If a miner chooses to leave, they can unregister and this bond will be returned. The system will automatically penalize miners for not voting or for voting incorrectly. If a miner's bond balance falls too low, it will not be allowed to vote. This bond mechanism helps ensure miners are committed to the operation and creates a motivation as a return on investment. Miners deserve compensation for doing the work of the system. Payments will be made to the miner's ECA from a smart contract, perhaps called a cashier. But how does the cashier get the funds to pay the miners? Well, customers are paying for service with their orders, so the system will allocate a portion of each payment and forward that to the cashier. Now let's take a closer look at the lottery and see how miners remain consistent. We imagine the lottery as a table that tracks miner votes. We know the miner's address, the block ID, and a Merkle hash value computed from the database as of that block. As time proceeds, Ethereum is regularly completing and publishing blocks and signaling all Ethereum nodes around the world. Let's pretend that Ethereum has just published block n-1 and begins work on block n. Within milliseconds, every miner receives a block completion event. Each miner does its database commits, calculates a hash, and sends it to the lottery at the same time block n transactions are being processed. Now imagine Ethereum completes block n and the miners begin block n plus 1. Then the lottery receives the first vote for block n. Before saving it, the lottery first examines all votes for the block n minus 1 and determines the winning hash value based on the majority of votes. The lottery then selects all the miners that voted correctly. It picks one of those at random to be the winner and sends it the reward. The amount of the reward is the sum of the miner portions of all the orders in the block. Our system motivates the miners for good behavior and penalizes them for bad behavior. If a miner receives a penalty, it will automatically resynchronize its database so that it will vote correctly going forward. One might wonder if it's possible that a lazy miner might cheat by simply watching for lottery events and copying a vote of another miner, rather than doing any work. Ethereum events are not published until the block has completed. Our miners are voting blind. A bad miner will not see the other votes until their block is complete. By that time it's too late to vote anyway, as the lottery and honest miners have all moved on to the next block. Previously I mentioned that miners act as a kind of bridge between clients and Ethereum. Clients need the services deployed on the miners to make application-specific queries. But when it comes to transferring money or making mutable changes to Ethereum, we can't delegate that ability because the miner will not have any client's private key and can't create a valid signature on behalf of a client. Ethereum does have an RPC mechanism that tethers mobile clients to an Ethereum node, but that's not acceptable here as the miner has to support all clients of the system, not just one. Our approach is to write the client software to use the same cryptography as Ethereum and form a raw transaction including the signature made from the private key held on the user's device. The client can send that to the miner, and the miner will post the data to the Ethereum network. A miner can view but not alter the transaction because the signature would then be invalid. A bad miner might simply ignore clients and just do mining. So for that reason we will incentivize miners to forward raw transactions by tipping them. That's enough detail about distributed application mining for the moment. So where did we get to really? We have simply used Ethereum as a platform for money and synchronization, and we've built our own application-specific layers on top of it. But our layer doesn't have the processing and storage limitations and can communicate across external interfaces. There's still much to decide. I hope you'll join us for future presentations regarding our Darchitecture concept. Thank you.